solving linear systems.
How?
Ooh! By elimination.
Sick.
All right. So we've done substitution. That was great. That was super great, especially when there was a coefficient of 1 on at least one of the variables, although it will work otherwise. But when there's not, solving by substitution can sometimes be not so great. And we might want to try looking at other methods to see what our personal preferences might be. So solving by elimination allows us to apply linear transformations to equations so that we can combine them to eliminate variables. Or a variable, sorry. The linear transformation that we will use here will be the multiplication of each side by a constant. Whoop whoop. So, what we're going to do is we're going to start by looking at these guys over here. And what we can do is we can write this equation in an equivalent manner, but it looks a little bit different by multiplying each side of that equation by some constant. And that's the same constant on both sides. Right, so if we go ahead and let's multiply both sides by, I don't know, pick a number.
2?
2, okay. Let's multiply both sides by 2. So if we multiply the left-hand side by 2, then 2x becomes 4x, 3y becomes 6y, and on my right-hand side, 12 becomes 24. This is an equivalent form of the equation. So that we can see that these equations are the same. We could do it by anything. We could multiply it by a large number or small number. Well, I'm going to move this down a little bit. What if we multiply it by a larger number?
10.
Oh, okay. Suppose I'll take your advice. Let's multiply both sides by 10. Alright, so 2x becomes 20x, 3x becomes 30y, and 12 becomes 120. Still an equivalent form of the equation. As long as we're doing the same thing to both sides, all is well. We could do the same with the other equation, right? If we have a different equation, same thing. What if we multiply by some sort of fraction instead?
Whoa.
Do you want to pick a fraction?
Yes, I do. I would like 1/2.
Okay, let's multiply both sides by half. Multiply both sides by 1/2. So 4x becomes 2x, negative 8y becomes negative 4y, and 20 becomes 10. So we can multiply both sides by a whole number, whether it's small or large, and we can multiply it by a fraction. What if we multiplied by, I don't know, let's say a negative number?
Ooh.
Yeah, let's get fancy up in here. What negative number do you want to multiply by?
-3.
Okay, so we can also multiply both sides by negative values. They do just the same. So 4x, positive 4x, becomes negative 12x. Negative 8x becomes positive...
Yeah, that's a y.
Oh, sorry. Negative 8y becomes positive 24y. And positive 20 becomes negative 60. Okay, so we can multiply by small numbers, by large numbers, by fractions, by negatives. All is same. We still get the equivalent form of the equation as long as we're multiplying both sides by the same thing. So that's going to be a key part of elimination here.
In solving by elimination, we are going to multiply, or positive multiply, one of the equations by something, maybe both equations by something. But there's infinitely many options. You can multiply by 2, by 10, by 1/2, by -3. We're going to pick one in particular. But to set this up, you need all your x's aligned, and your y's aligned, and your constants aligned. So if I'm going to tackle this one here, and I've got equation 1 and equation 2, I'm just going to rearrange them ever so slightly. So I like to have variables on one side. So here's 2x minus y, and then adding 5 to both sides. I've got 5 on the other side. And in equation 2, well, I just have to swap what side's what. So that's how we have to lay things out. Now, we might need to multiply these equations by something, but what we really want is for one variable to have same but opposite coefficient. Like if this x is 2, we'd want this one to be negative 2. Fortunately, in this case, with this one being negative y, the other equation has the opposite, positive y. The reason why that is handy is because if we have coefficients that are same but opposite, this step is huge. We stack the two equations, we add them together. Just straight up linearly. Yeah. 2x plus x is 3x. Negative y plus y is nothing. It's gone. And 5 plus 4 is 9. There is no y in that equation. There's only one variable. And if there's only one variable in the equation, well, we have the tools to solve that. We can, at this point, just straight up say x is 3, just by dividing both sides by 3. And if we have that, then we can plug into either equation to solve for, how you say, y. So if I sub into, I'm going to go with equation 2. It's a little easier on the eyes. And 4 is equal to x plus y, but we know x. In fact, we solved this equation before when we played with substitution. So we should get the same answer. Subtracting 3 on both sides, 1 is equal to y. And we can state our answer. xy is 3, 1. Dang, that was efficient. I love elimination. Elimination's the bomb.
Yeah, elimination's nice.
Yeah. Ooh, another example, hey?
Ooh, can I do it?
Okay.
All right, so we're going to start off by doing the same thing. We're going to label our equations 1 and 2 just so that we could reference them later on. We are then going to make sure that our coefficients are on one side. Personally, I like the order x first, then y. I don't know.
Yeah.
Just my own preference,
No, it's a good
alphabetical.
standard.
And then our constant on the other side. So for equation 1, just that little rearrangement becomes 2x minus 3y is equal to negative 6 because I've moved that 6 over. And then on the other side here, I'm going to add 3x to both sides. So I get 3x plus 2y is equal to 17. Now, if I am taking a peek here at my x coefficient, so I have 2 and 3, they are not the same but opposite, right? One's 2, one's 3, and they're both positive, okay? If I look at my y coefficients, again, still not same but opposite. Oops. Get rid of that. I have negative 3 and positive 2. So they're opposite, but they're not the same. So we have to pick either of the two of them, either the x or the y, to make them the same but the opposite. Since my y's are already opposite in terms of my coefficient, I'm going to try and make those y's the same. And this takes us back to what we were talking about earlier, is that we can write equivalent forms of these equations by going ahead and multiplying both sides by the same thing. So how do I make negative 3 and positive 2 the same? Well, I'm going to go ahead and I'm going to multiply my top equation, my equation 1, by 2, and I'm going to multiply my bottom equation by 3. That way I could have negative 6 as my coefficient for y in equation 1, and I could have positive 6 as my coefficient for y in equation 2. So that takes me to here. So 2x times 2 is 4x, negative 3y times 2 is negative 6y, and negative 6 times 2 is negative 12. And then in equation 2 here, I have everything multiplying by 3, so I get 9x plus 6y is equal to 51. Boop, boop, boop. Now I have those highly sought after same but opposite coefficients for at least one of my variables. Now we're stacked, and what we can do is we can straight up add these two equations together. Okay, so if I'm adding down the columns here, so I have 4x plus 9x, that gives me 13x. My negative 6y plus 6y, boom, she gone.
Whoa!
And then negative 12 plus 51, that gives me 39. Okay, so I have eliminated y in this particular case. Just for the sake of, I like working from left to right over here, so I'm gonna just continue on the left-hand side, just because I'm a little bit OCD in the way that I work. I don't want to go in a circle. So, 13x is equal to 39. I divide both sides by 13. And I get x is equal to 3. I have solved for x. I am pretty stoked about it, actually. And what I'm going to do is I'm going to take that value of x and substitute it into one of my two equations. It really doesn't matter which one I choose. And then solve for y. The only reason I'm going to substitute into to equation 2. The only reason I'm doing that in my own personal head brain is that y is already on one side itself. So I'm just going to do that because then I don't have to isolate y. I just have to divide both sides by 2 after. Do you feel? Okay, you felt.
Yeah, I definitely feel.
So I have 2y is equal to 17 minus 3x. But I know what x is. So 2y is equal to 17 minus 3 times 3, which is 17 minus 9, which is 17 minus 9, 8.
Nailed it.
Yep.
You should teach math.
Honestly? Thanks. And I end up with y is equal to 4. Now, I can't just leave x is equal to 3 and y is equal to 4 just there willy-nilly. I need to state my final solution. My final solution is a coordinate point, and that coordinate point is when x is 3 and y is equal to 4. Yeah.
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 Yep.
We could also talk about contextual problems.
Ooh. For example, Justin and Ryan. They used to be Manitoba's top doubles team for badminton. And you know what badminton people like to do? They like to bulk. They're huge. They're swole. So they're shopping for protein bars and jugs of milk. Justin's buying 20 protein bars, 2 jugs of milk for $63.30. And Ryan buys 27 protein bars and 3 jugs of milk for $86.70. And yeah, that's just their morning meal. That's how they do. That's what we do for badminton. Because if you ain't swole, then what is the cost for each protein bar and jug of milk? That's what we're after. We're going to need a let statement. Let me make a statement. Yeah, let's do it. Let. We need the cost of each protein bar. We need the cost of each jug of milk. I'm going to let P represent the cost of a protein bar. And I will let M rep the cost of a And I make my equations. Justin buys 20 protein bars, 2 jugs of milk for $63.30. So equation 1 for me says that 20 times the cost of a protein bar plus 2 times the cost of a jug of milk is 63.3. And according to Ryan Land, if you take 27 times the cost of a protein bar and 3 times the cost of a jug of milk, it's going to cost you $86.70. You know, and add 0. Neat, super swell, splendid. We have a chunk ton of options. We could do, like, we have the 2 and the 3. We could do same up here and just multiply by each one's opposite to get a common 6. I'm going to do something real wacky. I'm going to multiply this by a half. Because that will make this just an M. Yeah, this is going down. This is going down for real. And I'm going to multiply this. I would multiply it just by a third. The thing is, these have the same sign, and I need them to be opposites. So I'm going to go with negative 1/3 and see what happens there. Oh yeah, what else is happening? So 20p times 1/2 is 10p. 2m times 1/2 is just m. And 6330 times 1/2, well, you're going to have 3, and then probably a 1, and then, how many times does 2 go into 13? 6? 6 times?
6.5.
6.5 times, perfect, thank you. And then this other one, dividing everything by 3 or multiplying by negative 1/3. So positive 27p times negative 1/3 is negative 9p. Positive 3m times negative 1/3 is negative m. And 86.7 divided by negative 3. Now 3 goes in there like 2 times. And then remainders and stuff is like an 8. And then there's like this. Check it out. They same but opposite. Which means, woo! I'm ready to stack and add these. 10p plus negative 9p is just p. Positive m plus negative m is nothing. And then the difference between these two, if you're processing this mentally, like they're almost 3 apart. And you can work from there. If this was 20.25 more, then we'd be exactly 3 apart. So we must be that much shy of 3. 2.75. And if we have one of those, we can find the other. I don't know, I'll sub into, I'm going to go with 1. And in that case, 20. Heck, I can use my modified version of it. Redo. I can say 10p plus m equals 3165. So 10 of these protein bars, which are 275 each, plus m, 3165, and work from there. And subtracting 27.5 from both sides, we're around there. We have our value of p, we have our value of m, which means we have the cost of a protein bar, and we have the cost of a jug of milk, and we can respond. Nailed it.
Keep in mind that when you're doing these and you're taking a look at the answer key for eventually when there's a worksheet that you're working on, it really doesn't matter what you multiply your equations by as long as you end up with additive opposite coefficients for one of your variables. So you very well could have multiplied equation 1 by something like 3 and equation 2 by negative 2 so that you get plus 6m in equation 1 and negative 6m in equation 2. It really doesn't matter. So as long as you end up with additive opposites in your variables, you do what just feels right. Okay? There is some textbook practice that you should be taking a peek at, so that's page here. Just look at this. I don't have to read it to you.